Welcome back, students. Let's go back to section 3. We talked about the compound interest model and then logistic growth model. Now let's go ahead to radioactive decay model. Radioactive decay models are written either this way using the natural exponential function or using the base of 1/2. This expression and that expression are actually equivalent because this k value and this capital T value can be adjusted accordingly so that they are the same. By the way, this capital T is called the half-life. It takes capital T time unit, whether it is seconds or minutes or years, whatever. It takes capital T time unit till the initial quantity is halved. So when t is 0, then this whole thing is 0 power, so it's 1. So initial quantity is Q0. See, the initial quantity. When t is equal to capital T, then this whole thing is capital T over capital T. So it's 1 power, isn't it? First power. So it's Q0 times 1/2. So the half of the original quantity. And it takes capital T to become half. So capital T is called a half-life. It turns out that capital T and this k value here, the decay constant, they're related like this, and capital T is log of 2 over k is log of 2 over capital T, like this. It turns out like that, but I don't know whether this thing is really important for majority of the students here. If I had some physics students sitting here, maybe that's important. Oh, never mind. Yeah. Okay, all right. Let's go ahead with an example problem. The quantity of a radioactive material can be modeled by the following formula. Okay, all right. 21.2 times e to the negative 0.07 t, where t is measured in minutes. Estimate the initial quantity. Plugging t equal to 0, then e to the 0 power is 1, so this entire thing drops out. So the initial quantity is 21.2. Is it what? Grams or milligrams? I don't know. Whatever the unit. The quantity after 2 minutes, so plug in t equals to 2 here, and plug in t equals to 20 here, and punch in the calculators. So they're all direct computations. So initially 21.2 grams or milligrams. I don't know. I should have given you the units for those quantity. And then 2 minutes later, 18.4. And then 20 minutes later, 5.22 something. And then here's a graph going down like this. How many minutes later will the remaining quantity be 10 milligrams? Okay, I must be using milligrams for the weight units. Sorry about that. I should have specified in advance. So this whole thing is equal to 10, right? This thing is equal to 10. So that's the question, and you have to solve this equation. It's an exponential equation. Flip this number to the other side, take the log to remove this exponential, and remove this negative 0.07, and you're there. Okay? Like this. Setting equal to 0. Divide away the coefficient to solve for exponential. Now, removing exponential will require taking the log. So take the log to both sides, and then exponential is now gone on the left-hand side. Right-hand side, we gain the log. Before calculating this log, divide away by negative 0.07, and then calculate. It'll take about 10.74 minutes. In terms of seconds, 10 minutes 44 seconds, approximately. Yeah. Here's another radioactive decay model. This time it is written in the half-life model. Americium-241 is a radioactive substance used in common household smoke detectors. The radioactive decay of americium-241 can be modeled by the following formula, where Q0 is the initial quantity and time t is measured in years. So 432.2 years later, the initial quantity will become half. And that is one of the reasons people are using americium-241 for household smoke detectors. It goes down very, very slowly. So you can use it for a really long time, as long as you replace those batteries. You can use it for a really long time. And also, the radioactive radiation is not that strong, so it's okay to use. And then it does not produce. It does produce oligoradon so that you can inhale. That's pretty bad, but very little. So comparatively speaking, it's relatively safe. Of course, people are getting natural radiation from sunlight anyway, so something much smaller than natural radiation is not much of a deal. So people use americium-241 in household smoke detectors. Anyway, let's do math problems. Enough digression. Suppose that you have 10 milligrams of americium-241, so initial quantity is 10 milligrams, and then estimate the remaining quantity after 20 years, 200 years, and then interestingly 432.2 years. So that's half-life, so 1/2, and then double that, 864.4 years. So 1/2 and then another half, so 1/4 of the original. So these two you can figure out just by mental math. You don't need calculator. Just half-life and then another half-life. So 1/2 and another 1/2, so it's 1/4. But these two, well, you have to punch in the calculator to find out. Here in my answer key here, I did all those in, computation. As a matter of fact, no, the first two, I did direct computation by punching the calculator. So it turned out 9.684 milligrams, 7.256 milligrams, approximately speaking. And then C is just by half-life, so half of the original, so 5 milligrams. And wrong key. And then D is similar, another half-life later, so 1/2 squared, so 1/4 of the original. So 1/4 of 10 milligrams, so 2.5 milligrams. By the way, here's a graph measured from 0 to 3,000 years. Oh, it's going down, yeah, but very, very slowly. How many years later will the remaining quantity be 7.0 milligrams? So we'll have to set this equal to 7.0 milligrams, right? So starting from 10.0, and then that's equal to 7.0. Solving this equation, well, divide this 10.0 away so that you can solve for the exponential, and then you're going to take the log to bring this power to the coefficient. Ready? Okay, here we go. Divide this away so we get that 0.7, and take the log to get this power down to coefficient. So t over 432.2, power down to coefficient, times this log of 1/2 is log of 0.7. Now you can punch in the calculator to find out log of 1/2 and log of 0.7, but I'd like to postpone it. Divide this away, so log of 7 over log of 1/2. One more. Flip this one away too, so multiply over here to the numerator, and then punch in the calculator. I got about 222.4 years. So this is a typical way to solve an exponential equation using log, using natural logarithm. Power comes out as coefficient, and then what's left is just a logarithm of a certain number, which I can calculate easily with punching the calculator. flip all those away, and then we get the t value. We have another problem here, but it's kind of repetitive, so let's stop here. So we went through 3 types of example problems. First, compound interest model is an exponential model. Logistic growth model, relatively important exponential model. And a radioactive decay model, which too is relatively important. Maybe not important as logistic growth, but certainly more important than compound interest model, I think.